Okay, hello. So I'm Simon. I'm going to be talking today about serverless WebSockets at scale, specifically trying to answer the question, is AWS ready to provide serverless WebSockets at scale? So first of all, who am I? I'm Simon Tabor. I'm a software engineer. I work at DAZN, which is a live sports streaming company. Unfortunately, I'm a JavaScript engineer, not a Java engineer. I was expecting boos there, so not doing too badly. But luckily, there's no code in this talk at all, so hopefully won't be too contentious. I've been working mostly with high-scale, real-time companies for 7 years now. So when I can combine serverless, which is a technology that I love, and WebSockets, another technology I love, that's why I'm here today. So what we're going to cover is our requirements. So we're going to go through what we were looking for and what we're trying to achieve at DAZN. Going to give an analysis, an overview of AWS AppSync, do the same for WebSockets for API Gateway, the same again for AWS IoT, and then we'll give an overview of our solution and where we are at now, and then also give an analysis and hopefully some insight into the future and where serverless WebSockets will go. So to start off with, at DAZN, we're building a new feature called Key Moments. So the idea is that users can be watching a live stream or a catch-up game, and they can see these small dots on the scrub bar that will highlight key events and exciting moments within that game. So for example, the screenshot there is showing goal, but there could be penalties, there could be red cards, anything like that. And the idea is that they can skip around them and basically build their own highlights reel. So we started off by asking the product team, what requirements do they have? So first of all, we need to support live events. So most of our users will watch their games live as they're happening, because that's the most fun way to watch sports. So we need to provide these in real time. And on top of that, we actually have a requirement that users must receive key moments within 30 seconds of them happening. The reason for that is let's say your favorite players just scored an amazing goal. You want to be able to skip back to that immediately after it's happened, rather than waiting for, let's say, a minute or two before it appears on the scrub bar. And we also do need to support catch-up events. We have quite a lot of users who come and watch the games the next day, so we need to be able to support them, as well as supporting people who join a live game halfway through. So we translated these into some system requirements and what we actually wanted to achieve. So we wanted to publish updates to our users rather than have them poll for updates. And the reasoning for that is that we run on a lot of CPU-restricted devices, such as TVs. And whenever you're polling or making HTTP requests more often than every 30 seconds, the overheads involved actually do have impact. And for us, if our feature had any impact on video playback, we'd be turned off immediately, because a user would rather not have key moments than have a stuttery video. We also need to retrieve previous messages and subscribe to new messages at the same time. So this is so that we can support catch-up and also support live games. And as I mentioned, support coming through halfway through into a game. You want to see the key moments that have already happened. So maybe you could give yourself a quick recap of all of the goals that have already happened. And we also need to perform with high traffic on a global scale. We have millions of users. They're distributed all around the world, for example, Japan, Spain, Germany. And we really need to perform with spiky traffic all over the world. And that's really prevalent when we have millions of users that come online just before their favorite football team starts playing. Before then, we have relatively low traffic. They all come online just in the minutes before. So we converted these requirements into a really high-level diagram. So we thought, OK, we have our millions of users around the world globally. We want them to be able to request historical data and subscribe to updates. That would be handled by some service on AWS. And then that service would push those updates in real time to those millions of users, and of course also send them the historical data. And then for our backend side on the right, we want our DAZN services, which in this case is Key Moments, to be able to publish updates, ideally through some sort of simple interface like an HTTP post. We'd just say, OK, this key moment has happened. Please send it to all the users. So we started thinking about what we wanted that service to actually have, what functionality set we wanted. And WebSockets was one of the main ones. But why WebSockets? I think that this diagram shows it quite well. So a client makes a simple HTTP request with saying, I want to create a WebSocket. So that means because it's on top of HTTP, it doesn't get blocked by proxies or any sort of firewalls or things like that. Then the server says, OK, you can upgrade this connection, and it basically creates a persistent TCP connection. And then for any amount of time after that, you can have full duplex bidirectional messages. So the client can send messages to the server can send messages to the client. And this can be open, as I said, for any amount of time, in our case, at least the length of an entire soccer game. And then whenever one side closes the channel, it gets closed, it's nice and clean. So one of the reasons that we chose WebSockets over something like server-sent events, which is another alternative for sending real-time messages to clients, is because they're much more versatile as they enable bidirectional messages, and they also allow quite a lot more flexibility on the browsers, because browsers are only able to open around 6 server-side events channels, and you have to have one open connection per channel. It becomes a bit of a mess. And then why serverless as well? So I think this graph shows it quite well for us. So in the red, you have the capacity, the number of users that are online on the platform. And in the blue, the bars are how much capacity you'd have provisioned if you were using, let's say, auto-scaled EC2 instances. So whenever the blue bars are higher than the red, you have redundant capacity. You have wastage, basically. And whenever the red is above the blue, we actually have a service outage, because we can't serve that many requests, and therefore our users might even unsubscribe and cost us even more money. Serverless allows us to basically just follow the red line without even thinking about it. If we can make it so that we don't even have to think about auto-scaling configurations or how we try to deal with our unpredictable load, serverless is the way to go. So we went back to our high-level diagram, and we thought, OK, what solution could we actually put here to be this service on AWS? Who can do our undifferentiated heavy lifting, as AWS always says? And we found AWS AppSync. And I'm just going to read a few quotes from their product pages and how AppSync is actually sold. So AppSync is a serverless backend for mobile, web, and enterprise applications. Well, great, we're mobile, we have a mobile application, we're web as well, we're quite big, kind of enterprisey. 3 ticks there. AppSync uses GraphQL. Well, we weren't looking for GraphQL at all, but GraphQL is fantastic. It's really flexible. So as a bonus, big win, just added out of the box. It offers virtually unlimited throughput and storage that scale according to your business needs. So it can deal with our scalability concerns, and virtually unlimited as well. Hopefully that's good enough. And AppSync enables real-time subscriptions across millions of devices. We have millions of devices. We want real-time subscriptions. Tick again. Sounds perfect. So immediately we jumped in and we found some pros. And the biggest one there is GraphQL. And the reason for that is that it's so flexible. So we thought, how would we model our data as GraphQL? And this is a very, very basic high-level diagram of it. So in the center, in the blue, we have a fixture, which is basically just a sporting event between 2 teams. In this case, those 2 teams are Man United and Chelsea. And then associated with that fixture, we can have key moments. And those key moments can be a goal, red card, penalty, etc. And then to power our current feature that we want, we'd simply query out all of the key moments associated with a fixture and then deliver those to the user. But the real value comes in when we want to build features in the future. When we want to build new features on top of this data set, we'd be able to potentially query out, OK, find me all of the goals that Chelsea have scored in their last 3 matches. Without having to remodel your data, without having to build new API endpoints, you'd just let your front-end clients request it, and it would just work. So GraphQL, really powerful, really wanted to be able to use it. But we quite early on found some cons. And I love diagrams, so I put a little diagram together of how we'd like authentication to work with AppSync. And to put it simply, we want our back-end services that are basically detecting these key moments to authenticate using IAM, because they're already running, they already have a role, and if we can just authorize that role to be able to publish messages to AppSync, our problem's solved. We don't have to think about it anymore. But then on the front end, we really don't want them to authenticate using IAM, because there's a lot of overhead involved in getting an access token, a secret key, signing the requests, and everything along those lines. However, AppSync supports custom authentication methods by triggering lambdas, but because there's a limit on Lambda of 500 new concurrent executions per minute, we are limited and can't use Lambda authentication, because if we try to scale up to millions of users in a few minutes, we'll hit that limit, everything goes boom, basically. So we're forced to use one of these out-of-the-box methods, and AppSync only supports one at any given time, which means we're forced to use the lowest common denominator, and we're forced to do what works for the front-end users and have an API key on both sides. It doesn't look too bad until you realize that, OK, we create these two API keys, one for the front end, one for the back end, and then we have to hard code the API keys in our GraphQL resolvers, basically in our AppSync configuration, to say, OK, the back-end key is the only one that's authorized to actually publish, write data, and the front-end one is authorized, obviously, to get data. So this is horrible, because it means that things like key rotation and all of these things that you just expect from security, we then have to start thinking about again. So it turned into a bit of a mess. But we thought, for now, we can deal with it. Hopefully, AppSync's quite new. We'll get improvements in the future. And then we thought, OK, how do our front-end clients actually query for the existing data and subscribe to updates? And did another little diagram. It's quite complicated, right? So first of all, they have to make a request to subscribe. Then they'll receive a response from AppSync, and that subscribe response will include a WebSocket URL to connect to, and also the tokens and anything else required to open that WebSocket and subscribe to the topic. After it's received that response, it's able to open the WebSocket itself, and then subscribe to the topic once that WebSocket is open. And then only after all of that has been completed, we can query data and then get the response, so we can get our existing key moments. So there's actually a lot of steps involved for the front-end clients to just initialize, basically. And because of the way that it's split into two different sections, subscribing and querying, we can't cache the query, because we'll immediately get race conditions unless we start waiting for set timers and stuff. So if the query data is stale, say we subscribed after the cached data had been stored, we could potentially miss key moments, and then our users will start complaining, you're not showing a goal, etc. And it would be very difficult to debug. But we thought, again, we'll keep on building a proof of concept, we'll keep on battling through this. And then we thought about global deployment. How do we actually make this thing work globally for our millions of users rather than just a single AppSync? Another diagram. We have millions of users, again, distributed globally. They could hit Route 53 latency-based routing, which is basically AWS's DNS provider. And then that could distribute the users across any number of AWS regions, and in each region would have a single AppSync. And the problem here, well, it doesn't look like one at first, but the problem arises when, because the user has to make two requests, so one to subscribe and another to query, they could technically be routed to different AppSync distributions for each request. And what that means, again, is that we can end up with global replication race conditions, which are really messy. We don't really want to get into them. You can't replicate data globally without latency. So it could mean that a user could query data from one region and subscribe to another. It would be very, very rare for that to happen. But when you're doing these sort of things billions of times in a month, it will happen. And I don't want to be the engineer on call when you get someone saying, I'm missing this key moment, and you just don't know where they've been routed to. So we were aware of this, but not a total deal breaker. We could probably get around it. But with the global deployment, AppSync works best when it's backed directly by DynamoDB. So it can query Dynamo directly. And we started thinking, how would this implementation actually work? So each user performs an AppSync query on connection. as I've said, to get the existing key moments, each user will perform a query. AppSync will then map that query into a DynamoDB query. So in our case, it's only a single Dynamo query, but in other cases, you could have multiple queries for a single AppSync query. But Dynamo has a limit, and that limit is 3,000 read units per second per partition. And this is a hard limit. This is one of the few AWS limits that you can't move in any circumstance whatsoever. And because of the way that we store our data, each fixture, each event's data, is stored on one partition. So what that actually means is that we end up being limited to 3,000 new users connecting per second per fixture. And it's a bit of a mouthful, but at the end of the day, what that means is that it would take 1 million users who are connecting over 5 minutes to query all of that data out because of this limit. So at our scale, it actually becomes quite a serious issue. And when we're hitting these Dynamo limits, we'll be serving basically 500 responses. And those users will have to keep on retrying and not have key moments until that's resolved. So this was quite painful, really. And we started to think, well, there must be solutions to this, right? We must be able to get around this. The first one we thought of was, could we use DynamoDB on demand? It's a great service. It basically allows us to not have to provision capacity with Dynamo. Well, it would help with our costs. It would help with our capacity provisioning itself, but it wouldn't help with this limit. This limit still exists with Dynamo on demand. And then could we potentially split our data out so that it's stored across multiple partitions? Well, no, because unfortunately, the minimum read units that each query consumes is 1. So if we split the data for a single fixture across 2 partitions, we'd just consume 1 unit in each partition rather than just 1 unit in one. So it became a bit of a mess. And we thought, well, this is perfect data to be cached. We were always thinking it should be cached. We're serving the same data to millions of people. Why would you always go back to your actual data store? Why not cache it? But we first looked at using CloudFront or any sort of CDN. But because of the query and subscribe logic that I mentioned before, we can't cache it at the CDN layer. And if we tried to, we'd have to basically query twice based on whatever we'd tuned the TTL to be. Again, it becomes a massive mess. So we took that out. Too much logic for the front end, too much complexity. And then we looked at DynamoDB Accelerator, or DAX. And DynamoDB Accelerator is fantastic. It's a service that basically has the same API as Dynamo, but adds like sub-millisecond response times. It has automatic invalidations of items. And we were like, OK, maybe we can use this. But number one with that is AppSync has no native support at all for DAX, which would mean that we'd have to use a Lambda to query DAX. And then we hit Lambda scaling limits. But on top of that as well, even if it did have support, we actually want to cache a query and invalidate a query, which DAX doesn't support. DAX doesn't support invalidating queries. It only supports caching them for a fixed time. So again, we'd end up with race conditions. So that was out as well. And then we thought maybe we could just try to keep it simple and use something like Elasticache or Redis/Memcache. But again, we'd have to write a Lambda to actually query that data. And again, we hit Lambda scaling limits. So we came to the conclusion that one does not simply cache AppSync. It's not easy. Something that quite potentially should be easy was too difficult for us to actually achieve. And this is actually an issue with quite a lot of GraphQL services anyway. Caching in GraphQL is difficult because the whole point of it is that there's complex queries that change between users. So we're like, well, there must be at least some solution. So we talked internally, we talked with AWS, we talked with quite a few people. What can we do to work around this, at least temporarily? And the only solution we could come up with was duplicating the data, all of it, n times when writing it to Dynamo. So let's say in this case, we chose n to be 100. Whenever we receive a key moment, we'd store it 100 times and just have it totally replicated. Then we'd have the front end select a random number between 1 and n. So it basically run math.random. And then it would go, OK, anything between 1 and 100, and then it would query for that data, so basically sharding it onto that partition, which would mean, yes, we resolve our query load. If we had 100, we could go from 3,000 to 300,000 for our maximum capacity. But, I mean, come on. It's a mess, right? You've got no single source of truth. You're basically paying for so much capacity that should be cached. We have higher latency because we're always going to the data store. And we have no single source of truth. Again, I don't want to be the engineer who's on call when you get a user saying, I'm missing a key moment, and you have to ask them, well, what partition were you querying in that case? Because the user will obviously never know. So we were like, nope. We kind of ran away from Dynamo and AppSync at that stage. We kept on building our proof of concept because the core logic still made sense. We still needed to build our key moment services that sit on the right here. But we started looking for alternatives. What other service could fit on AWS? And then reInvent 2018 happened, and there was the announcement of WebSockets for API Gateway, and all of our faces in the office went like that. We were very excited to hear this. So again, I'm going to read a couple of quotes from their announcement blog post about how they sell WebSockets for API Gateway. So historically, building WebSocket APIs required setting up fleets of hosts that were responsible for managing the persistent connections that underlie the WebSocket protocol. Well, yes, building WebSocket APIs is difficult because you have to manage these fleets of hosts. And the persistent nature of the connections is what makes it really difficult, because with cloud infrastructure, we're kind of used to having throwaway infrastructure where if something's not performing as we expect, we turn it off. With WebSockets, you would have to disconnect all of your users, and then they'd have to reconnect. So you have real user impacts whenever you want to change anything around. Now, with API Gateway, this is no longer necessary. API Gateway handles the connections between the client and the service. It lets you build your business logic using HTTP-based backends such as Lambda, Kinesis, or any other endpoint. Well, get in. That's fantastic. We basically are getting a proxy between WebSockets, which are operationally really difficult, and HTTP, which, as developers, we're all quite comfortable with. I think everyone here can build an HTTP endpoint. So we immediately jumped in, and we found some pros. It's really flexible, and that means that you get access to send messages to each individual connection. So let's say that Bob basically connects to our service. We're able to use his connection ID to send messages directly to Bob at any time. And that means that it's incredibly versatile. You get far more control than AppSync. It doesn't try to solve all of your problems for you. You build your own service using API Gateway as your kind of proxy. And it's fully serverless. You can use a Lambda now for all actions that happen on your WebSockets API. So every time a user connects, disconnects, you receive a message, you can just fire a Lambda, or you could put it into Kinesis for asynchronous processing. Really powerful. And then we quite quickly found cons. And it's around broadcasting. So as I mentioned, it's designed for sending specific messages to specific users, which means that, again, I can target Bob and send the message directly to him. However, it's not designed for broadcasting a single message to millions of users. And I'll show you why and how we can find that it's not designed for that. So first of all, we need to invoke a Lambda for each connection as it comes in and store the state in Dynamo. So we'd have to store the connection ID and what match they're watching so that we could query it out later. That's bad enough because we'd hit potentially Lambda scaling limits again. But to make it even worse, to actually send all of those users a message, we have to query all, let's say there's 1 million users watching a single game. We have to query out all 1 million rows from this database, and then we have to loop over them one by one and make an AWS API call for every single one of those connections. There's no ability to send messages in batches, bulk, or broadcast at all. So to achieve this, we'd end up having to put our messages into a queue for asynchronous processing. Turns into a total mess, and it means that it's no longer real time. You can't do 1 million API calls to AWS in a few seconds. So that was over quickly. We were really excited to start off with, and then just basically had to give up quite early. And we came back to our diagram again. We're like, OK, what service could fit here? And when we were investigating and using AppSync, we found that AppSync is actually powered for the real-time subscriptions by AWS IoT. So we thought, well, why can't we do that? Why can't we use AWS IoT to power our subscriptions and then maybe add the extra functionality that AppSync was missing? So we had a look at their product pages to see how it was sold again. So AWS IoT can support billions of devices and trillions of messages. Well, that's orders of magnitude above what scale we need. We could serve everyone in the world for that, so fantastic. It makes it easy to use AWS services such as Lambda, Kinesis, and S3, so it's got the integrations again. It supports HTTP, WebSockets, and MQTT. Obviously, we're interested here mostly in WebSockets, but the ability to use HTTP is fantastic because it means that we could have fallbacks. And we're really interested in the message broker, which is a high-throughput pub/sub message broker. So we want to be able to publish messages and have all of the subscribers, millions of subscribers, receive them. And even better, it supports messaging patterns ranging from one-to-one commands to one-to-one million or more broadcast notification systems. Well, that's exactly what we want, but the flexibility that it can support the high end and the low end means that we could use it for almost any application that we build in the future. So we jumped in again, and the main pros are that it's really mature. It was released in December 2015, whereas everything else is around a year old or less. So it means it has a huge number of features. It's received a lot of adoption. Unfortunately, many of those features are totally irrelevant to us because it's an IoT solution. It's not an application WebSocket solution. But some are, including good monitoring. So one place, for example, where AppSync was totally lacking was in monitoring. We could only see the 2xx, 4xx, and 5xx response count. We couldn't see pretty much anything else. IoT had pretty solid monitoring there. And then we found cons again, of course. So we looked at the protocols and the documentation, and we found that for authentication, MQTT and HTTPS can use a simple client certificate. So it would simply transfer that to the client when they actually load up our application, and then they can be authenticated using that certificate. But HTTPS and MQTT over WebSocket, and the WebSocket bit being where we're interested, requires SIG v4, which basically means we need to be signing the request with an access key and a secret key, which takes us back to where we were with IAM authentication. We can't deal with a user having to go through that process. It's too heavy on them and could cause stuttering. And even worse, to really securely get them an access key, we'd have to set up all of our users incognito. Then when they load the application, they'd have to log in, get the token, sign the request, and then connect. So again, you've got too many steps involved, really, to actually just getting some basic data. So we gave up again, came back to our diagram again. And this time, we changed our approach a little bit. We stopped trying to think, OK, what single service on AWS can solve all of our problems and mean that we don't do any work? And we thought, OK, let's just build something ourselves by putting together a lot of other AWS managed services. And we called it Pubby because naming things is really difficult, and it publishes things. It's quite simple. And we started off by mapping out our requirements, so what we actually wanted this service to do. We wanted to use a shared WebSocket connection for subscribing and for querying. So we wanted to not have any of these global scale race conditions. We didn't want to have one request to query the existing data and another to subscribe. We wanted to do it all over the same WebSocket connection, so it's nice and efficient. We also wanted minimal operational overhead. So we wanted to be serverless wherever we could be, but potentially avoid serverless in a couple of places where it's too difficult. And ideally, it would be generic for use by other applications. So because we're solving this problem, there are loads of other applications at DAZN that require publishing messages to millions of users. So why not make it so that we can share it within the company and hopefully also make the architecture shareable externally as well? So the next thing we moved on to was the architecture itself. And we started by planning out the subscriptions. So here we have our millions of users again. they all connect to CloudFront, so there's a single CloudFront distribution for them. That then maps to Route 53 latency-based routing, which allows them to connect to the region that is by latency closest to them. And then in every region we run in, so this could be any number of regions really, we have an application load balancer which distributes the requests across an ECS service. So we have a number of tasks running in each region. And then those tasks connect to an Elasticache cluster, which is running Redis. And we use that Redis cluster for a cache, but also as our pub/sub message broker, so that we can actually send messages to each task so that they know to send a message to all of the connections that they currently have open. So we thought, OK, this makes sense at a high level. How do we publish messages? So on the far left here, we have our external services, which are key moments, but hopefully other services in the future. They make a simple HTTP post request to API gateway, which triggers a Lambda. And that Lambda is very simple. All it does is stores the data in Dynamo. So we have our single source of truth. And then as soon as it's been successfully stored, it publishes a message onto an SNS topic. And that single SNS topic is subscribed to by another Lambda that runs in every region that we use. So that means at the moment we could have any number of Lambdas subscribed to the same topic. They all trigger in parallel. And each one within its own region will invalidate the cache, obviously make sure that stale data is no longer being served, and then also publish a message onto the pub/sub message broker. And that would mean that each task running in that region can handle that message. They can send the message to all of the users that are connected, and then also indicate that the next time someone requests the historical data, we'll requery it back from DynamoDB. So we have our single source of truth as well, so it's easy for us to build and debug. So altogether, hopefully not too over-complex, we have our architecture, and it works with global availability and failover. So we thought, OK, well, we need to run load tests on this. We need to make sure that it will actually work. And we successfully achieved a load test with over 5 million concurrent connections, so 5 million open WebSockets, and also managed over 1.3 million new connections per minute. So we managed to achieve pretty high scale here. We did all of that with a P99 latency of 5.7 milliseconds, and that compares to AppSync, which on some basic tests we found had a P50 latency of 35 milliseconds. So we're really a lot faster here. And then we thought, OK, we shouldn't be testing the happy path all the time. Let's test when something goes wrong. And this happened. So in the red, we have connections to EU Central 1, the AWS region. And we limited that region to only be able to handle around 1.5 million connections. So what happened was we hit 1.5 million, the service became overloaded, and then our number of connections dropped to 0 before US East 1 could take over, which is pretty awful. We really don't want that. That shows service instability. All of our users got disconnected and had to reconnect. We're like, why would that happen? We've got latency-based routing. Surely that would work. But no, latency-based routing measures the latency between your users and the AWS region, not your users and your service, which means that if your service is performing badly, it can still be serving traffic. But we did find that there's a way around it, which is to use CloudWatch health checks. So we can now have a CloudWatch alarm that triggers this failover. We implemented that along with a few sanity things so that the task couldn't become overloaded, and got a graph that looks like this, which is much nicer. So we hit our capacity limit in EU Central 1, and then that region basically is able to detect and say, I'm overloaded, and I'm also unable to scale anymore, fail over to another region. And then you can see after about 60 seconds, which is the DNS TTL, the rest of the connections get routed to US East 1, and we're able to handle the capacity. So looking pretty good there. But what conclusions can we make here? And is AWS actually ready to provide serverless WebSockets at scale? First of all, Pubby. It deals with a very specific use case. That specific use case should be shared. And it basically means that you can publish messages to millions of users. But what you can't do is publish a message to an individual like you could with, say, API Gateway. The service can be used by other teams at the zone, and hopefully the architecture can be replicated and used elsewhere to provide WebSockets to more people. And we've achieved high availability with seamless regional failover. And all of that is using a single shared native WebSocket connection, which means we can support all of our devices without adding extra CPU overhead and potentially implementing or increasing the amount of video stuttering. What about AppSync? Well, AppSync is incredibly powerful. GraphQL is exceptional and basically gives the front end a lot of flexibility and functionality out of the box. But the key moments requirements, what we were trying to build, they're really simple. All we want to do is get a list of items that happened queried by a fixture ID. We really don't want any of this complex relationships or any sort of complex query structure. And as well as that, subscriptions are arguably the weakest part of GraphQL. They're one of the newest parts of GraphQL. They're not terribly well spec'd, and that means that there's a few things that are a bit confusing, and again, we're unable to query the existing data over that same subscription. And as well as that, managed services do have their downsides. So as much as most of the time we'll choose to use an AWS service if it's available, they do have downsides like monitoring and testability, for example. But this will probably improve as the service matures over time. But I would personally recommend AppSync for any service with many related models or a really complex data structure, especially if I was starting something from scratch right now that wouldn't have millions of users from day one. I think AppSync would be a really good choice. What about WebSockets for API Gateway? Well, I think it opens a huge opportunity to use WebSockets. I think it's WebSockets for the masses, really. Unfortunately for us, the lack of broadcasting is just an immediate deal breaker. We can't use it at our scale. But if you had something that didn't require broadcasting to millions of people, maybe had even just chat rooms of, say, 100 or so people, it would be absolutely fine. And it's brand new. It was released in December last year, which means that there will be updates, there will be improvements. Hopefully one of those is being able to bulk send messages. What about IoT? Well, it deals with massive scale. We've got the billions of devices, trillions of messages. We wouldn't even have to think about the scaling aspect here. But any solution needs to be specifically designed for IoT. Believe it or not is in the name. IoT is designed for Internet of Things services, not for application WebSockets or something else like that. So whatever we'd do would have to be forcing their functionality to work for us. And quite simply, the authentication just doesn't suit us. If we were already using Cognito or already had access keys on the front end, maybe we could make it work. But for our situation, it was just too much. We were going to go into a rabbit hole and end up very upset. So what about the future? So here's our current architecture, running in production, got millions of users, working really well. But it's not serverless. So we want to kill the non-serverless part. Everything else here we're quite happy with. Maybe in the future we'd be able to change from a single region for the publishing aspect to have regional failover. But we already have multi-AZ failover, so it's working at the moment. But if we put a really mission-critical service, we'd add multi-region there. But the really important bit is where the red cross is. I would love to be able to swap all of that, which was a lot of overheads, a lot of auto-scaling configurations, and all of those things that we really wanted to avoid with an AWS service. And I'd hope that that service is something like WebSockets for API Gateway, and we're able to get around, first of all, the scaling limit with Lambda. I know that Firecracker could improve Lambda quite a lot, and also get around the fact that we can't broadcast. So that's it. Thank you. I think I have time for a few questions. No? Oh, you're making it easy. Great, thank you.